Everyone, and good day. My name is Kishan Kumar Analaki Muthukannan, and my team Lim Yi Cheng and Marcus Yong Chun Hao also involved this computer architecture assignment. Okay, in this video, I will present about how to evaluate a complex arithmetic expression step by step. We will convert it from infix to postfix notation, illustrate it using a stack diagram, and finally design 0, 1, 2, 3 address machine instruction. This will help understand operator precedence, calculation order, and how many computers handle arithmetic efficiently. Let's get started. So, the program execution expression we design is this. M equal bracket H at B multiply A bracket sub bracket T divide Y bracket add bracket J sub C bracket multiply bracket S at N bracket at B. This expression is considered complex because it uses 10 variables H, D, A, T, Y, J, C, S, and B. So it's 10. It includes four types of operation: addition, subtraction, multiplication, division. It contains brackets which require careful handling of operator precedence. So let's go. Step 1 is we multiply DA because multiplication has higher precedence than addition. Step 2, then we will add H to become like this. Step 3, we will divide T divide Y and subtract it from the previous result like this. Step 4, evaluate J sub C and S and N separately, then multiply become like this. Step 5, we will add the result of the step 4 to the result of the step 3, become like this. Step 6, finally, we will add the B to this result. Step 7, the final result we will store at the M, becoming like this. So this is how we design the program execution expression. Okay, now we will see the postfix notation. Postfix notation is way of writing expression where operators come after operands. It is easier to evaluate using a stack, especially in computer. So see. So first, we will move this first. D multiply A first. Okay, first we will move D. D multiply A become a D. A multiply because multiplication have the highest precedence. So we will move out this first. Actually, you can move anything first lah. For example, like you want move this S at N first or H at D first. It depends you want to move which bracket, but I will move this one first. So third one is becoming like this. We will move to in front of multiplication becoming like this. H D A multiplication and add like this. After this, I will move this bracket T divide Y become a T Y divide like this. First move the inside bracket first. Inside bracket first. Please don't move these three things. I show you this, this, this. Don't move first. first move the bracket inside the bracket. Okay, after that, I move this JC sub becoming like this. After that, move SN add becoming like this. It's actually very simple. You just move to front, move to behind move to behind like this. After we settle all the bracket inside the bracket, then we can move the outside of the bracket like this: sub, add, multiplication, add. Then I move this multiplication first from this to I move to SNX multiplication. Then I move this one, this sub I move to front of divide lah, become TY divide sub. After that, I want to move this add. After that, I will move to front of this here. Okay, now finally we will move this add B becoming like B add, like this. And then we will store this all to the final result in M, coming like this. This is how it's work. Postfix notation. Okay. Now we move to stack diagram. Using postfix notation, we can evaluate the expression using a stack. Each operator pops the two top operands, perform the operation, and push the result back. So I will step-by-step evaluation using stack. So first I will push H, second I will push D, third I will push A, and then I will multiply D multiply A, because each operator pops the top two operand. So I will D multiply A, and then I will add this to H add D multiply A, coming like this. Okay, after that we will push T, push Y onto stack diagram, and then we will divide T divide Y onto stack diagram like this. And then we will sub T divide Y to the previous result, becoming like this. After that, we will push J, push C, then we will sub J sub C, becoming like this, to the stack diagram. After that, we will store this, we will store add to the previous result like this. Okay, I will push S, push N, and then we will add S, add N, becoming like this, and then we will multiply the previous result, coming like this. After that we will push B, and then we will add to the previous result like this. Then finally we will store this result to the M, the final value to the M, pop M, so becoming like this. So this is how stack diagram is work. Okay, now we move to zero address machine instruction. A zero address machine does not use any register. All calculations are done using a stack. Every operand is pushed onto the stack. Operators automatically pop the top two operands, perform the operation, and push the result back. So first we will push H. We will push H onto the stack, push D onto the stack, push A onto the stack. Later we will multiply D multiply A, and then add H, then become like this, and then push T onto the stack, push Y onto the stack. Later we divide T divide Y, and then we subtract previous result. Push J onto the stack, push C onto the stack, subtract J sub C, push S, push N, later S at N becoming like this, multiply the previous becoming like this, later add with the previous result, push B onto the stack, add B, after that store all the final result in pop M. That's how it's work. A one address machine use one main register called accumulator, short form AC. All operations are performed with AC and one operand from memory. Immediate results are stored in temporary registers. So first, we will load D first to the accumulator. Later, we multiply A and we'll store temporary accumulator. Then we add H to the accumulator. Then we store at R1 first. Later, we load T to accumulator. Then divide Y to the AC. Then we sub the result. We sub the result R1, and then we store R2 immediately. After that, we load J to the AC, sub C, then we store to the R3. After that, we load S, we add N, and then we multiply R3, and then we add R2 to the previous result, add J sub C, multiply S and N. Then after that, we add B. Then all the result we will store into the M. Now let's move to two address machine instruction. Two address machine use two operands per instruction. The result override the first operand. We use register to store intermediate results. So first, we will move R1 D. So first, we will store the D to the R1 directly, and then D multiply A, store R1 directly, and then add H, H add, store R1 directly, and then move R2. We will store T directly in R2. After that, we will divide Y and store to R2, and then sub the previous R1 result to the current R2 result, becoming like this. And then we will move R3 J, store the J into the R3, and then sub the C, and then we will add another store. It means we will store another R4. We will store S, then we will add N, and then we will multiply the previous R3 to the R4 current, and then we will add R1 to the R3. It means the previous result add this result. It means and then we will add R1 B, the final result at B, and then we will move M to the R1. That we will store all the final result in the M. Now let's move on. Three address machine instruction. Three address machine have three operand, a destination and two source. This is most flexible and efficient. Let's step by step explanation. First, we will multiply D A and directly store to the R1, and then add H plus D multiply A and directly store to the R2, and then R3. We will T divide Y. Later we will sub directly like R2 and R3 like this. Later we will store J sub C to the R5, and then add S at N, store to the R6. Later we will also do the same things. We will directly multiply the R5 and R6 and store to the R7. Later we will store the R8 with the previous result and R7 together. We will add B. Later we will store all the final result in M. That's how it's work. In conclusion, the infix expression was converted into postbit evolution step by step using a step diagram. 0, 1, 2, 3 address instruction were also generated to show different ways a machine can execute the same expression correct. That's how from us. Thank you for watching.